Welcome back. So we're talking about k-means clustering algorithm, and we sort of have seen the drawbacks of the algorithm and where it works well, where it doesn't work well, and we started relating k-means to a Gaussian mixture model. So what happens in a Gaussian mixture model, if you see, is that, just coming back to the same example, right? Okay, which we were talking about. Okay, so your clusters are modeled using Gaussians. Meaning what? Clusters are modeled using the means and the variances. Okay, all right. Okay, and not just by the mean. Okay, which is what k-means does. Okay. So your centroids are just, your models are just Gaussians. It's just, the models are centroids only, but no covariances are considered into account. Okay, all right. Which is why, this particular model can be actually, you can think of this as, still, even though they are using Gaussian mixtures, they are hard partitioning only. So therefore the expectation maximization is an improvement on top of this. Okay, all right. So let's see. So we know the multivariate Gaussian. I've shown you the univariate Gaussian. In a multivariate Gaussian, you would have instead of the one stand variance that you see in the univariate Gaussian, you will have a covariance matrix, right? And this guy is typically actually should be in the denominator. This is just written as an inverse or -1/2, right? And instead of x minus mu square, you'll have a x minus mu transpose times x minus mu, because it's a matrix, and each one of these are matrices, and this one is also a diagonal matrix. Okay, so the diagonal matrix which contains the variances along its diagonals. Okay, the maximum likelihood estimates of this particular Gaussian model are the sample mean and the variation. Okay, we are going to skip this. Okay, but the idea is each cluster will be modeled using one of the Gaussian bell curves. Okay, now what happens is you use the parameters which describe the cluster. So what are the parameters? The parameters, because you are using the Gaussian, right? So your parameters are the mean of the cluster, the covariance of the cluster, and the size of the cluster as well. Okay, so what really does it mean? It means that this is where the probabilistic assignment comes in. So I have like one distribution, then I have another distribution, then I have another distribution, then all are Gaussian, right? Okay, so I have something like pi. Okay, now this pi is nothing but the probability that belongs to a cluster. Okay, now remember these clusters are Gaussians only. Okay, so what could happen is I have a point, it could have a pi value, like you have a pi 1 value and a pi 2 value and blah blah blah, pi n value, right? And these values could be different from each other, correct? Okay, so based on whichever pi value is the largest, you assign the data point to that particular cluster or that particular Gaussian mixture model. Okay, so that's the whole idea. Okay, it's not, and therefore what you do is for each example data, right, we compute a responsibility index, and that responsibility index is nothing but the relative belongingness of one particular data to a Gaussian model. Okay, and that responsibility index is computed in the following fashion. You have the normal density function, which are represented by the data point itself and the parameters mu and the covariances, right? Multiply that with the pi, which is nothing but the respective belongingness of the cluster to that, of the data point to that particular cluster, and then normalize it over all clusters so that your responsibility index is a value between 0 and 1. Okay, all right. So therefore, if a particular data point is very likely to be under some particular Gaussian mixture, which is a cluster, the weight is very high, right? So, and the denominator is just a normalizing factor. Okay, all right. So this is the Gaussian mixture model. Okay, all right. So typically we do this repeatedly. So what happens is you have the expectation. So you are talking about the expectation maximization algorithm, right? So what is the expectation? The expectation is that a particular data point belongs to a cluster, right? So for that particular data point, I mean, so typically I'll tell you what we are trying to do here by going back to the example. What we are trying to do here what we'll try to do is we repeatedly compute the expectation, iterate it, so that the discrimination of this cluster, the vertical ellipse from the horizontal ellipse becomes more visible, which means you are going to shift the ellipse in such a way, you are going to align the ellipse in such a way that after certain number of expectation iterations, you would begin to see the discrimination between the data points more clearly, okay, unlike this. Okay, so we do have this responsibility indices, or which are probabilities, right? So we start with some assignment of these probabilities, right? And we continue to update the parameters, which are the mean, the variance, and the size. Okay, all right. So and then what we do is, for each step we do a maximization. So if we do the maximization operation, which is nothing but taking the, doing the gradient ascent and stuff like that, but if we maximize, then each maximization step will update the parameters. Okay, so the parameters that we are going to use, if you recall, the parameters that you are going to use are n, pi c, mu c, and sigma c, right? Okay, so you are going to need to update these parameters, right? So you can see, when you update the parameters, you can compute the total responsibility allocated to a particular cluster, right, which is NC, and then the fraction of the total assigned to a cluster. And then you compute the weighted mean of the assigned data. So the weighted mean of the assigned data is nothing but, the total responsibility of the clusters, corresponding to a particular data, averaged out by the total responsibility allocated to that particular cluster. Okay, and then you also compute the weighted covariance. So you use all that to increase the log likelihood. So each expectation step will increase the log likelihood of the parameters. Remember that this is the size of the cluster, this is the normal density function of the Gaussian on the data point, and the mean and the covariance, right? Okay, you take the log of it, take the sum of all that, and what is expected in the expectation step is that as you iterate, okay, it will increase the log likelihood of the model. In other words, your models are Gaussians, right? What does it mean? It means that the likelihood of one particular data point belonging to that model will increase. Okay, all right. And we keep on iterating until convergence. So basically this is just a gradient ascent method, unlike the gradient descent method. Okay, we will give a brief so this data is collected, I don't recall the I think it's University of California, Irvine, or so this data is an experiment where people try to figure out the healthy patients versus anemic patients. So we have their red blood cell hemoglobin concentration. So these are the groupings of the healthy patients, okay, and these are the groupings of patients which are anemic. All right, but however, I mean, it's kind of difficult to segregate the two, right, because you really don't know the class levels. So what we do here is, when you first do a cluster, okay, this is the first iteration of the expectation maximization, right? I mean, you have the mean over here. So it's particularly, if you want just one, so you have the green cluster and you have a red cluster, there is little difference, because you would want to, because your healthy patients are also sparsely distributed, you have a dense cluster somewhere over here, and the anemic patients are also sparsely distributed, right? So if you do a cluster like this, what you can see is there are a bunch of data points which are not captured by either of the clusters at all, and you see an overlap between the two clusters, right? Okay, I mean, this is what you are going to get if you do a k-means. Okay, all right. However, what the expectation step does is that repeatedly tries to segregate the green from the red. Okay, all right. So here, after 3 iterations, what you can see is that the green starts shifting. Okay, so also this is visible between the means of the two clusters, right? This is the mean of the green cluster and this is the mean of the red cluster, right? Okay, and this is the Gaussian mean. Okay, all right. we keep on increasing the iterations after, and you can see a much better cluster. So the dense data points, the points which are really dense, these are the normal patients, right? Okay, the dense data points, they start segregating. Okay, and the red cluster is also doing, because you are actually capturing the parametric information of the healthy patients. As a result, the red one has also started elongating itself and started capturing the anemic patients, okay, which are not normal. Okay, all right. You keep on doing this. Okay, so this is the 5th iteration. In the next iteration, you can see you already start seeing much better results. Okay, because the idea is that your healthy patients are actually here. Okay, and these are your anemic patients. So you would want to shift the green cluster towards the densely populated healthy patients and the red cluster to the sparsely populated, anemic patients. Okay, then we keep on doing this. Now at the iteration number 15, we are seeing much better results, right? I mean, we see that the healthy patients are here, the anemic patients are here, and probably if we keep on doing this, we are not going to see too much improvement. So probably there is a stopping criteria based on the number of iterations and the number of allocation of the data points. And if you plot the log likelihood function as a number of iterations, you will also see that up to 15 iterations is like a steadily increasing function. It's almost monotone, right? However, after the 15th iteration, as you increase the number of iterations, you really do not see much increase. It gets flattened out. Okay, so this will tell you this will actually be a trade-off. You can continue doing the iterations, but your accuracy or the cluster purity will not increase much, right? So this is probably a good indication of where to stop, right? And you can say that you have attained a reasonable convergence. Okay, all right. So it's a general expectation maximization is a general framework. It is not right to call it an algorithm per se. Okay, and it corresponds to maximizing the expected complete log likelihood. Okay, all right. So basically, the Gaussian mixture models, it's an improvement on the Gaussian mixture model by having that soft assignment operation. Okay, all right. And there are different other versions of expectation maximization and Gaussian mixture models, but we are not going to talk about that now. Okay, all right. Like for example, Gibbs sampling, infinite clustering, and so on and so forth. Okay, all right. So that brings us to the end of expectation maximization, Gaussian mixture model, and k-means. So basically, what I wanted to do was I wanted to show the k-means as a special case or a variant of the expectation maximization algorithm. Okay.